So today we're going to look at Euler's formula with proofs and applications. Then we're going to look at de Moivre's theorem with proofs and applications. Like I said last time, there are a lot of proofs for this complex number section. Okay, so what we want to show is that e to the I theta is equal to cos theta plus I sin theta. Now this will look very, very weird to you at first, because we know how the exponential works. You put in some real number, you get your exponential out. Now, inside this function, we are putting a complex number, right? Because r theta, that's going to be imaginary, so we can take that as complex. So the question is, how do we put a complex number into a real valued function? Okay. So question. How do we put a complex value into a real valued function? Right? So e to the x, real number goes in, real number comes out. Now we're trying to put a complex number in, and we see we get a complex number out. So how does that actually work? So the way we do that is using the Taylor series. Yeah. So as it is, the exponential function, we don't know how to put a complex number inside. But if we look at the Taylor series for e to the x, so e to the x, so this is under the proof now. So e to the x is equal to the sum, n goes from 0 to infinity, 1 over n factorial, x to the n. You see, we're mixing a whole lot here. We've got polar coordinates going on, we've got series going on, and complex numbers going on. Okay, so we've got this Taylor series. Now, on the left-hand side, that's the exponential. On the right-hand side, we can just treat that as a polynomial. So on the left, we can put in I theta. On the right, it's just powers of complex numbers. We know how to do that. Okay, so on the left, we're going to put in I theta. And on the right, we will put in r theta as well. Now, for every power of n, we can calculate that. That's a complex number to some power. We know how to deal with that, right? R squared is -1, and then you just carry it. Okay, so let's look at this right-hand side and try to simplify this. Simplify this right-hand side. And by simplify, I mean, what is I theta to the n? How does that simplify? Okay, so what is this? Okay, so let's start off with a few values of n, and then we try to see a pattern. Okay, like we did with the original Taylor series. So n equals 0, that's our starting point. So this will be I to the 0, but anything to the 0, that's 1. Okay, so anything to the 0 in the real world, that gives us 1. For complex numbers, it's the same thing. Okay, what about n equals 1? Now we have r to the 1, that's just I. Okay, nothing funny there. Okay, what about n equals 2? So now we have r squared. What's that going to be? -1. And then n equals 3. So I cubed. So we just multiply the previous thing by I, so we get -r. We'll do one more, and then you'll see the pattern. N equals 4, r to the 4. So we multiply that previous one by I, so we get 1. Okay, now let's have a look at the pattern. Firstly, these even terms are 1, -1, 1. So just make a little note there. Even terms are 1, -1, 1. So blue, that's for even. Okay, and then in pink, let's look at the odd terms. So we have I minus R. You can guess what the next one's going to be. That'll be I. So these are the odd terms. So you see the even ones alternate. 1 minus 1, 1 minus 1, and so on. So the even terms alternate plus minus 1. Okay, so plus 1, minus 1, plus 1, next one will be minus 1, and so on. Okay, and then the odd terms, it's I minus I minus I. They alternate in the same way. So the odd terms alternate plus and minus I. Okay, similar to the even terms. Yeah, so this gives us a natural way of splitting up the sum. So instead of having the sum over everything, we're going to have the sum over the even terms that alternate plus 1 minus 1. And we're going to have the sum over the odd terms that alternate plus I minus I. Okay, so from this, we split the sum into two parts. So we're going to have an even part with all of the even terms, and we're going to have an odd part with all of those odd terms. Okay, so let's do that. So again, we have e to the r theta is equal to the sum. Now we're going to list out all of the even ones. So that will be n goes from 0 to infinity, 1 over 2n factorial, because it must be even. Now remember, this even one alternates plus 1 minus 1 plus 1 minus 1. So we need a minus 1 to the n. Yeah, so we get plus 1, minus 1, and so on. Then we have theta to the 2n. Right? Again, must be even. Let's look at the odd part now. So the odd ones alternate plus r minus I, and so on. So we can write it as plus I in front. The sum, n goes from 0 to infinity, 1 over 2n plus 1. Remember, it must be odd. Then, again, it must alternate, plus 1 minus 1. So we need a minus 1 to the n. And finally, theta to the 2n plus 1. Okay, so in blue here, this is all of the even terms. And then here we have all of the odd terms. And then the I we took out to the front. Okay, but what is that even part? What is that the Taylor series of? It's cos, yeah. And the pink one? Sine, exactly. So this is going to be equal to the even part, that was just cos, plus, and then we have the I in front, we can't forget that. And then the pink part, that was the Taylor series for sine. Okay, end of proof. Okay, that's the proof for Euler's formula. And this method works in general for complex functions, which we'll get to later. So this will be the first complex function we're looking at. So other complex functions, for example, if we had sine of a complex number or cos of a complex number, how do we work with that? We write out its Taylor series and then substitute the complex number in. Okay, that's the general method for working with complex functions. But we will get to that later on. Okay, but an important note. Okay, now we have to remember way back to beginnings of last year when we did even and odd functions. You remember those? Yes? No? No? We better go back and recap that. Remember, for the exponential, e to the x, the even part was e to the x plus e to the x, e to the minus x over 2. So this was e to the x plus e to the minus x over 2. Remember that? Anyone? Yeah. Okay. And then the odd part, that was e to the x minus e to the minus x over 2. You remember that one? Yeah. What did we call the even part? That was hyperbolic cosine. And the odd part, what did we call that? That was hyperbolic sine, sinh. Okay. Now, it's just a note to keep in mind. We'll get back to this later. But just look at that bottom one and look at the top one. Notice the similarities. So in the bottom, we have e to the x, where x is real. Remember, complex is z. Other letters, those are real. So e to the x being real, we get hyperbolic cosine plus hyperbolic sine. Now, what happens when we put in something that's imaginary? R theta, that's imaginary. We get cos and r sine theta. Please note the relationship between those two. Okay, so we'll have a look at this in a lot more detail later on. But for now, just look at the similarities. Okay, so we'll write it out here. So e to the x is cos x plus sinh x. And then e to the ix. So instead of theta, I'm just putting x so we can see the relationship there. Is cos x plus I sine x. Okay, please put a box around that. Okay, it turns out, and we will prove this later on, that the exponential, the sine function, the cos function, the hyperbolic sine function, and the hyperbolic cosine function are all the same function. Yeah, so we looked at them all differently, but they're actually all the same thing. Yeah, and we'll prove that later when we do complex functions. So just put a little star, see you later in complex functions. Okay. Any questions on this? Yep. Over here. This one is cos. If you're using imaginary, if it's real, it's hyperbolic cosine. Yeah, we'll prove later those two are actually the same thing. Yeah, but for now, just look at it being similar. Okay. Now, using Euler's formula, we can rewrite the polar form of a complex number, and from now on, we will be using this form. So we can write it out using Euler's formula, but when you're actually doing the calculations, you'll be using the sine and the cosine. Okay, so remember some complex number z was r cos theta plus I sine theta. Right, that was just straight polar coordinates, nothing funny with that. But cos theta plus I sine theta, we now know and we've proved that that is e to the r theta. So we can write the polar form as r e to the I theta. Okay, please put a box around that. Okay, and then the electrical engineers in the class, please put an exclamation mark there. You will be using this heavily later on. Okay, I've got a special sub-chapter just for you guys. Okay, so please put a box around this form of a complex number being some r e to the r theta. You'll use that quite a lot later. Okay, so the way you'll be using it is more like this. So you'll have some a e to the I theta, or can write it as omega t plus phi, something like that. So when you're working with your electric currents and so on, you write it as amplitude, frequency, and phase. Yeah. So electrical engineers, just copy this bit down. So this is amplitude, frequency, and phase. Okay, so when you're working with your voltages and your currents and so on, your lecturer will say amplitude and frequency and phase and all of that, but you need to be thinking about this. Yeah. Okay, now that's I'll have a special subchapter for you. We'll look at later. Okay, because the sad thing is your lecturers later on, they assume you know everything beforehand. And then people don't go through it, and then they say, oh, no, study it yourself. Okay, but I'll go through it with you guys. Okay, so this here, polar form, so you can choose between the two. So you can write your answer like this, z equals re to the r theta. That's fine, totally acceptable. But if you want to find the real part and the imaginary part, then you have to use that first equation, right? Cos theta, that gives you the real part. Sin theta, that gives you the imaginary part. Okay, so just have a look at the wording of the question. Okay, but there's plenty of questions like that in the tutorial, okay, to go through. Right, any questions so far? All good. Okay, next, De Moivre's theorem. Okay, proof and applications. There may be more applications, but we're only going to be looking at 3 of them. Please make sure you know this proof. We'll be using it later on in the applications. Okay, so what is this theorem? Let's say we have some complex number z in polar form. So we can write it as r cos theta plus I sin theta. Yeah, normal complex number in polar form. Now, what we want is to find a power of this complex number. So we want to find z to the n, where n is some number. So we want z to the n. So this is going to be r to the n cos theta plus I sin theta to the n. Now, r to the n, that's easy. We can do that. Cos theta plus r sin theta to the n, that's going to be quite difficult to calculate, right? Imagine we have cos theta plus r sin theta to the power 5. You're going to have 5 brackets you need to multiply out. Okay, but De Moivre's theorem says, no, we don't have to do all that work. We can just write it like this. Okay, so De Moivre's theorem tells us that n in the exponent can jump down to the theta like so. Which is very helpful because if we have some complicated power, like 4 or 5, whatever power, all we need to do is multiply the angle. So the power turns into angle multiplication. Okay, which is a whole lot better to work with than powers. Okay, let's have a look at the proof. Okay, so we start off with the complex number in polar form, but we're going to write it using Euler's formula instead of the cos theta and the sin theta. So we have z is going to be re to the I theta. And what we want is this z to the power n. So we're going to raise both sides to the power n. So we have that. Now, what we're going to do is write out that right-hand side there 2 different ways, and that will give us our proof. Okay, so there's no calculations or anything. All we're doing is writing that out 2 different ways, and we've got our answer. So let's write it out the first way. So the first way is by replacing the Euler's formula there with cos theta plus r sine theta. And that's to the power n. Now, all we're doing is just changing the way we look at this. If we have an exponential to some power n, we know that the n can just multiply inside. So this is the same thing as r to the n, e to the I n theta. Because it just multiplies inside like that. Does everyone see that? Okay, now e to the I n theta, we're going to write that out like we did for cos theta and r sine theta. So that's r to the n, cos n theta, plus I sine n theta. And that's it. Okay, so all we did is we wrote it 2 different ways, and that's the end of the proof. Okay, very easy proof. Any questions? You're good. Okay, let's have a look at the applications. So number 1, we're going to be looking at powers of complex numbers. Okay. Number 2, roots of complex numbers. So if n is like 3, then it's like cube power. But if n is a half, that's the same thing as roots, right? So if n is a third, that's cube roots and so on. So depending on n, you can either do powers or you can do roots. Okay, and finally, we will be proving some trig identities. Okay, similar to the ones that you covered in high school. Okay, but here we're proving them using complex numbers in a much easier way. Okay, let's have a look at the first one. So powers of complex numbers. Okay, so we'll do it by example, give you an idea of how the calculation goes. So let's say we have z is equal to 1 plus I, and what we want is z cubed. Now, you could write it repeatedly, so you could have 1 plus I times 1 plus I times 1 plus I. That's a lot of work. You can try it out yourself, but we're not going to do that. We're going to use this de Moivre's theorem to write it out in a couple lines. Okay, so to use this, we need this in polar form. Okay, the 1 plus I must be in polar form. So we need to find r, we need to find theta. So that's going to be the roots of 1 squared plus 1 squared. So that will be root 2. Theta, that will be tan inverse of 1 over 1. That will be pi over 4. Okay, so we've got r, we've got theta, and now we can write out this power. So 1 plus I to the n will be r to the n. Okay, right, this was the n from the z to the n. So we're looking for cubed, so n is 3. Then it will be r to the n, so that will be root 2 to the n, in this case it's 3, then it was cos n times theta. So it will be 3 times the pi over 4. Plus I sine. And then remember over here, on the right there, it was n theta, so 3 times pi over 4 again. And we're done. That's it. Okay, so if you want to calculate the cube roots, you just need to find r, theta, and then you just substitute. Okay, and you all have your calculators. It's easy to put in cos 3 pi over 4 and sine 3 pi over 4. You get your answer. All right. Any questions for this one? All good. Okay. Number 2, roots of complex numbers. Okay, so let's say we have some complex number z, and what we want is the nth root. So, for example, the square root, cube root, fourth root, we want the nth root. So z is some complex number. We want the nth root. Well, let's put low n. So depending on the n, it's whatever root. So square root, cube root, fourth root, fifth root, and so on. Okay, now very big exclamation mark. The root function is multi-valued. Okay, so what does that mean? So if we have the cube root of the complex number z, we are going to get 3 answers. If we are looking at the fourth root of the complex number, we are going to get 4 answers, and so on. So there are nth roots of a given complex number. Okay. Again, if it's the square root, there's going to be 2 answers. If it's the cube root, there are going to be 3 answers. Fourth root, 4 answers, and so on. Okay, a little bit of notation. We write the roots of a complex number z. Okay, so we look at the nth roots of this. So this is z to the 1 over n, nth root, as w0, w1, w2, up to wn minus 1. Okay, so that is the notation that we'll be using. So some z to the n, 1 over n, nth roots of z. We're going to have n answers, and we're going to label them w0, w1, 2, 3, up to wn minus 1. So starting from 0, we have n of them. Okay, so how do we get these roots over here? Well, we use that de Moivre's theorem again. So the kth one, so wk, is going to be equal to r to the 1 over n. Because remember, we're not taking powers, we're taking roots. So n becomes 1 over n. Okay, then we're going to have cos of theta plus 2 pi k over n. Again, we're not timesing by n, we're dividing by n, because it's roots, not powers. Plus I sine theta plus 2 pi k over n. And this k will then go from 0 to n minus 1, like we have above. Yeah. So here, this plus 2 pi k, we're using the fact that these complex numbers are periodic. Remember, we said that last time. Okay, you remember from last time, we could add the 2 pi or the 4 pi. We get the same complex number. So we have to add the 2 pi k to that. Okay, we don't have to do it for powers, but we do have to do it for roots. Okay, so please remember this addition here. All right, any questions so far? You're good. Okay, so example. Find the 3 cube roots. Okay, so it will always go together. If it's cube roots, there's 3. If it's square roots, there's 2. So it always goes like that. So find the 3 cube roots of z equals I. Okay, so let's have a look. We need to find r, we need to find theta, and then we need to find these w0, w1, w2. Okay, so r, that's just going to be 1. Theta, that will just be pi over 2. Okay, so we have r, we have theta. Let's substitute to get our wk. So this will just be 1 to the 1 over 3. It just stays 1. So it will be cos pi over 2 plus 2k pi. And we're looking at the cube root, so we need to divide this by 3. Plus I sine pi over 2 plus 2k pi. And again, we need to divide by 3. Okay, so what you're going to do now is substitute k equals 0, k equals 1, k equals 2, and you're going to get the 3 roots. So we're going to have w0, w1, w2. Okay, there's only 3 of them. Okay, w0, what do we get? Okay, get your calculators, work it out. W0. Yep. Pi over 2. That's the angle for I, because I is going up. Okay, let me go to Desmos, I can show you. Remember where I is on the complex plane? It's y is 1, x is 0. Over there. Real axis, imaginary axis. You remember that? Yes, no, from yesterday, was it Tuesday? Okay. Anyway, the vertical, that's the imaginary axis. So 1 unit along the vertical is I. And remember back to polar coordinates, that angle is pi over 2. So there, that's 1 along the imaginary. Root 3 over 2. Pi 5. Cool, thank you. W1. Yeah. And last one, W2. Yep. 0 minus R. That's right. Okay, so we have our 3 roots there. Now something interesting and not so important for you guys doing engineering, but it's interesting. If we go to Desmos here and we plot them, we see something interesting with how their roots are spread out on the complex plane. So let's write out this e to the I fraction pi over 2 is over 3 plus 0 times 2 pi. We need in complex number. Okay, so we have one root over there. Okay, then we copy this for the other one. So this will be plus 1 times 2 pi, and then the last one is plus 2 times 2 pi. Can you all see the dots there? Okay, so what we have is all of these roots are actually spread out on the unit circle. Okay, evenly around the unit circle in the complex plane. Okay, so one of the roots is at the bottom there, and then we see the others form an equilateral triangle. Okay, that's with 3. If we had the fourth roots, what shape would that be? Square, yeah, because it's equally spaced around. And if it was the fifth roots, then we'd have a pentagon going around. Okay. So just something interesting about the geometry of it. The roots are spaced evenly. Okay, around the unit circle. I.e. equilateral triangle. So in this case, it was the unit circle, right? Because this has modulus 1, so it's a unit circle. If it was a difference r, then obviously the circle would have that, whatever that radius is. Yeah. But in all of the cases, it will be equally spaced around. All right. Any questions on finding the roots? You're all good. Okay. Last thing for today, proving some trig identities. Okay. So we're going to use de Moivre's theorem again, but we're going to use it for unit complex numbers. So the r will just be 1. Okay, so if r is just 1, what do we have? We have cos theta plus r sine theta to the n. Again, r is 1, special case. And then what do we have on the other side? This will just be cos n theta plus I sine n theta. Again, special case, r is 1. Now, we're going to focus on that right-hand side there. We've got cos n theta and I sine n theta. Notice it's not nicely separated into the real part and the imaginary part. So here, this is the real part. And this is the imaginary part. Okay, so the right-hand side is separated nicely. The left-hand side is not. Okay, so the idea, let's say we wanted the value of cos 3 theta. We wanted that trig identity. So on that right-hand side there, we put n as 3, and we want the cos of 3 theta, so we would take the real part. On the left-hand side, we also take the real part, and that will give us the trig identity. If we wanted sine 3 theta, on that right-hand side, we would say n is 3, and we would take the imaginary part. Then on this left-hand side, we would also take the imaginary part. Okay, so the idea is that cos n theta is equal to the real part. Remember, the real parts and the imaginary parts. We did that a while back. So that is the real part of cos theta plus r sine theta to the n. Okay. And sine n theta will then be the imaginary part. Yeah. So again, real parts, put that in blue, that goes with cos. And the imaginary part, let's put that in pink, that goes with sine. Okay. So we're going to do two cases. We'll do it for the double angle identity for cos 2 theta and sine 2 theta. We know what those are already. Then we're going to look at the triple angle identity. You probably don't know that, but we'll prove it. Okay, so the double angle trig identity. Okay, so what we want to prove is the identities for cos 2 theta, remember cos squared minus sine squared, and sine 2 theta, 2 sine theta, cos theta. So we want to prove cos 2 theta is cos squared theta minus sine squared theta. Okay, you've used that lots of times. And the sine 2 theta, that's the 2 sine theta cos theta. Right, you've used those lots of times. Let's prove them. Okay, so what are we going to do? Well, we look back at our equations here. We're looking for the case where n is 2. Okay, so on the one side, we're going to have cos 2 theta plus I sine 2 theta. Okay, that was on the one side. And now on the other side, this is going to be cos theta plus I sine theta squared. Okay. Anyone lost? Okay, good. So let's expand this out. It's just something squared. Easy stuff. Square of the first term, it's cos squared. Plus 2 times the product of the two. Plus, and then the second thing squared. But that has an I. R squared is minus 1. So it's minus. Okay. Now we're going to group together the real parts and the imaginary parts. So square brackets for the real parts. Plus I. And then square brackets for the imaginary parts. Okay. Now what did we want? Cos 2 theta, that is the real part of whatever we have here. That was squared. Okay, it's the real part of all of that. And that's just this first bracket. Okay, and we know, right? That's correct. Okay, now sine 2 theta, what's that going to be? That will be the imaginary part of whatever we just worked out. Yeah, and that will be that second bracket there, the one with the R. Yeah, done. Okay, so we proved the two double angle identities with one complex equation. Okay, any questions on this? You're all good. Okay, we're going to do one more with the triple angle, and then we'll leave it at that for today. Yeah. So you probably don't know what it is. So we'll just say we want cos 3 theta, whatever it is, we don't know yet, and sine 3 theta. Okay. So if we had triple whatever the angle is, like the previous one, we had double. Okay, so what do? Oh, same thing as before. We write this as cos 3 theta plus I sine 3 theta. Using de Moivre's theorem, the 3 we can write as the exponent. So this will be cos theta plus I sine theta cubed. Okay, now we need to expand this out the long way. Does everyone know Pascal's triangle? Okay, I'm not hearing any no's. You don't know it. Anyone else? Hands up if you don't know it. Okay, let's go through it. No, if it was just one of you, I could explain it afterwards, but we'll go through it. Pascal's triangle. You really haven't seen it? Okay. Oh, that's fine. We'll go through it. So this is just on the side. This is not part of this. So Pascal's triangle, let's say we have... Okay, there's a lot of talking for students who don't know what this is. Okay, so we have a plus b to the n. Okay, so what we want to do is try and expand this out. Okay, right? You know, if it was cubed, you expand it out, if it's squared, and so on. Okay, so how do we do that? Well, this is equal to the sum. K goes from 0 to n. N choose k. A to the n minus k. B to the k. Right? Binomial theorem. You know that, right? You don't know binomial? Okay. Okay, well, I'm not going through all of that. You do that in your own time. Okay, but what we want to do is find a simpler way of finding those coefficients. So these coefficients here. Okay, so that's just the choose function. You know that from metric probability and counting and all of that. But we're going to find a simpler way of working those out, and that's using Pascal's triangle. Okay, so what we do is we form a triangle where right at the top we put a 1. Okay, so we put a 1. Then on the next row we put a 1 and a 1. 1 and a 1. And then on the next row, it's the sum of whatever's above it. So we start with 1 again. And then what's the sum of everything above? It's just 1 and 1. So it'll be 2. And then we put a 1. Then for the next row, we have a 1. And then the sum of the terms above is 2 and 1. So there'll be a 3. Then a 3. And then a 1. Okay, so how do we get what these coefficients are? So this first row is when n is 0. So a plus b to the 0, that's 1. This next row is when n is 1. So what's a plus b to the 1? It's just a plus b. So it's 1 times a plus 1 times b. Okay, this next row is when n is 2. What's a plus b squared? A squared, 1 times a squared, plus 2 times ab, plus 1 times b squared. So it's 1, 2, 1. And then the next one is n is 3. So if I have a plus b cubed, how does that work? So a plus b cubed, it's going to be 1 times a cubed, plus 3, that's the next one, a squared b. The next one's also 3, so 3, ab squared. And then the last one is 1, so it's 1 times b cubed. Okay, so that's the binomial theorem, that's Pascal's triangle. You work on that yourself. Okay, so what we're going to do now is look at the cubed case, like we just had at the bottom. So remember what these coefficients were? 1, 3, 3, 1. So keep that in mind. So it's going to be 1 times cos cubed. Plus, what's it going to be? Next one. What does it start with? 3 cos squared. And then r sine theta. I is attached to the sine theta. Plus, the next one's going to be 3, then it'll be cos, and then r sine theta squared. Good. And then the last one, the coefficients are 1, so it will be r sine theta cubed. Okay, now we have some simplifying to do. So cos cubed is just cos cubed. We can leave that alone. Plus, we have an I over there. Let's bring it out to the front. Okay. Next, we've got an r squared in there. That's going to be a minus 1. So this plus becomes a minus. Next, we have r cubed. What's that? Minus I. Yeah. So let's look at the real parts and the imaginary parts. So this is the real part there, along with that. The imaginary parts will be the ones with the I. So that will be this and this. Okay, so finally, cos 3 theta, that will be the real parts because it's cos. So it will be cos cubed and that middle term over there, minus 3 cos theta sine squared. So this is cos cubed minus 3 cos theta sine squared. Okay, is everyone okay with that bit? All good. And then finally, sine 3 theta. Sine goes with the imaginary part, so we take the ones with the I. So that will be 3 cos squared sine minus sine cubed theta. Okay. Now, very big warning to all of you. This last step here with sine, we take the imaginary part. If you write your answer with an I give you 0 for everything. Okay. The imaginary part does not include the I. I said that in the last lecture and the lecture before. Okay. Warning to everyone. If you write an I for this last term here, it means you do not understand what the imaginary part is. You don't understand complex numbers. I give you 0 for everything. Okay. Any questions on this? You're all good. Okay. Any questions on the other complex number stuff we covered today? Yep. Yes, that is directly from, let's go back up here, Euler's formula. There. Okay, so Euler's formula, the real part is always with the cos, the imaginary part that is with the sine, because it always has the I in front there. Okay, any other questions? The quiz. Okay, so the quiz, the MCQ will be on the polar form. So you're just matching up the complex number with the polar form. And then the written part will be on these De Moivre's theorem applications. Okay, so powers, roots, and this last bit with the trig identities. Okay, there's 2 questions that I picked. Okay, any other questions? Right. Sorry, I can't hear you? Yeah, no proofs, no. No, so it's just matching up the complex number with the polar form, and then 2 of these applications that we did. So powers, roots, and the trig identities, I just picked 2 questions from that. Okay, so the remaining topics, it will be complex functions. That is not in the textbook, so I hope you write down all the notes for that. Complex equations, again, it is not in the Stewart textbook. And lastly, solving differential equations. That will be specifically for the electrical engineers. Okay, so you need to pay very close attention to that. The others, it's just something more for the exam. Okay, so let's just make a note of that. So you can read up on the weekend. Okay, so complex functions. Complex equations. Using complex functions in integrals. Remember integration techniques? They're back. So remember when we did partial fraction decomposition and we factored the bottom part, right? Now we're factoring them over complex numbers. So we had the quadratic, irreducible, and all of that nonsense. It's all back. And lastly, solving DEs. Okay, and then this is electrical engineering. So specifically, you'll see that a lot. But the next physics module, so if you're doing the physics modules next year, you'll be using this. Okay, but they don't teach it to you in the physics class, so we're going through it. So it's the physics module with waves and electromagnetism. Okay, if you're picking that module for next year, okay, you start off with that. Okay, but the complex functions, please read through that for the next lecture. Okay, any questions? You're all good. Okay.